There
you go.
We're off and running. Thank you.
Thank you.
All right.
I think you're good to go, Terry.
Oh, sorry, I didn't realize. It doesn't show me this recording. All right, so, okay. The thing that is kind of amazing about this very simple formalism is that actually, if you just take the classical boxes, like for example, the C swap box, and you add in these peak boxes, that is actually the full power of quantum computing. You could build a quantum computer. So if I think about it, not mathematically, if I imagine I just stack these boxes up. I have these boxes like the ones with 3 holes. Maybe I have some other boxes that have, there's other famous boxes like C0 boxes and C swap boxes. If all you do is just throw in some of these peak boxes, you lift yourself from the power of classical computing. Remember we said C swap has all the power of classical computing to the full power of quantum computing. But moreover, you can do it in a way in which the mathematics is really only a very little bit more complicated than the thing that I showed for the 2 peak boxes, for stacking 2 peak boxes in a single ball. So you can get by just using rules of basic arithmetic. So let me give you a sense of how that works. You kind of have to have one extra rule, which is how do you deal with the case where you have more than one system. So previously I said, well, let's consider cases where we have like the C swap box. But what if I have my C swap box and I'm going to drop through it states that are not fixed states of definite color, but maybe I have a ball that's black, and then I have a cube that's in the midst of being white, black, for example, and then a pyramid that's white. Okay. So now I need to add to my set of rules, like how is it that I deal, like what is this situation here? I know that the C swap says something like, well, if the ball is black, swap the colors of the cube and the pyramid, but how am I going to see that, write down the formal rule for dealing with this mathematically? And the answer is, in quantum mechanics, the answer is the tensor product of 2 vectors. And tensor products are a tricky thing, I think, when you first experience them. The rules in the MIST are a little bit easier, because it's very much like in arithmetic, if I took 5 times 4 plus 3 times 7, for example, I would say, oh, well, that's the same as 5 times 4 times 7 plus 5 times 3 times 7. Okay. And so my initial state here of the MIST before it goes into the C swap, I do something very similar. I treat this as a little bit like the number 5. This is a little bit like 4 plus 3. Okay, this is very similar to what I did up here. That superposition is a bit like addition, and this is a bit like 7. Okay. And so I say, oh, the initial state of this MIST before it gets dropped through is like black, black, white, white, comma, black, black, white. Okay. And so I've dealt with multiple systems by kind of, in some sense, replacing the multiplication here by just stick the 2 images together. Okay. And now I'm going to drop this through the C swap. And now it's a bit like the juicer rule again. I just say, well, I just treat the 3 configurations in the MIST separately. So this, the rule for the C swap said that if the ball is black, then swap the colors of the cube and the pyramid, but the cube and the pyramid are both white, so the swap colors look the same. But here, yeah. So I'll do basic quantum mechanics anymore. Here I swap the colors of the cube and the pyramid. So you can sort of think that it's like this ball goes through this like this, and you come out like this. And so we've essentially replaced doing tensor products with doing Cartesian products. And I think that's just much more natural. And then that's it. That's all you need. Once you have these rules, you can do any types of quantum calculations you want. Okay. Well, okay. At the end, I'll say a bit more about a couple of things that are sort of missing, but the basic structure is now there. Okay, so let me give you an example of how you can now teach one of these other kind of cool features of quantum mechanics. And the thing that I think is ultimately going to be the most powerful use of quantum mechanics in our lives is exponentially fast algorithms. So in the book, I do introduce an algorithm at the end of part 1 of the book, for which there's a exponential gap between what a classical computer can do and what a quantum computer can do. Ed Barnes came up with an even simpler version of the story. It's a little bit less obvious that there's an exponential gap, but it at least gets the point across that there's really a difference in power between a computer that only obeys the rules of classical non-mysterious physics, i.e. it's made up from boxes like the C swamp, and a computer in which I'm allowed to throw in peat boxes. Okay. And so I'm going to just tell you how that story works. Okay. So teaching this, I'm going to change the story a little bit. We set up a game. Okay. And since I'm in Australia, we can imagine we're playing this game in Australia. Okay. There's the Australian flag for you. And basically the game is that you get locked in a hotel room like this, like where I am. And there's 2 doors, and one door is black, and one door is white. Okay. And there's a big button that says open on it. Okay. And you're stuck in quarantine like me. Okay. You want to get out. And you're told, look, one of the 2 doors, if you open that door, you will be able to leave the room. Okay. But it could be the case that behind those doors, there's some Australian spiders. And if you know anything about the world, you should know that in Australia, you should not mess with the spiders. Okay. And so if you open the door that has the spiders, you're going to die. You're not leaving quarantine, you're going to die. And then they tell you, but to make it interesting, we have set up a little computer in the corner. Okay. Oh, and sorry, the other thing I should say is that if you press the button to open the 2 doors, they both open. You can't just open one door or the other. So what you really want to know is there a route, are there spiders behind either of those doors? Because if there are, I'm just going to spend my 2 weeks in quarantine and they can let me out. Okay. But if there isn't, well, then I'm going to leave. I'm going to escape. Okay. So they said, well, we've got a nice computer for you over here, and this computer can tell you whether or not there are spiders behind one of these doors or not. Okay. All you got to do is, okay, this computer, you have a black ball here that you can drop into it. And then over here, you have you can drop in either a white or a black cube into the second hole. And you pick the color of the cube to match whichever door you think you want to check whether they're spiders. And if there are spiders, so if you drop the white cube in, and there happen to be spiders behind that door, then the box will indicate that to you by applying the not operation, i.e. flipping the color of this black door. Okay, so it's a bit like a controlled NOT gate or something like that. And the cube will just come out whatever color you dropped in. But you're only allowed to use this box once. Okay, this is the spider box. Okay. Now the problem is that because you can only use the box once, you're only going to be able to be sure what's behind one of those doors. Okay, you can say, I think maybe there's spiders behind the black. So you drop in the black cube, and you might end up certain what's behind one of the doors, but you can't end up certain about what's behind both of the doors. And so therefore you're basically stuck, because remember, if I press the open button, both doors are going to open, and I'm going to get attacked by the spider if it's there. Okay. So we really want a way of working out, like, behind both doors, I just want to know, like, are there spiders or not? I don't need to know where they are. I just want to know, are there spiders there at all? And if there's not, well, then I can just go through. And if there is, well, I'm just going to sit here in my quarantine. And so the magical thing, so this is a game which you just cannot win without the magic of quantum mechanics. The magic of quantum mechanics lets you do the following. You take your spider box, and you do the same sort of basic thing here, but you stick a peak box. At both the entrances and the exits of this spider box. Okay. And the claim is that you will now be able to tell whether or not there are spiders behind either of these doors, okay, in only one use of the box. Okay. Whereas classically, you would have had to use the box twice, but you can't. So how does it work? Well, in the first step, we have this black ball and the black cube go through the peak boxes. Okay. And so they evolve to a mist, which is white, comma, negative black, times white cube, comma, negative black cube. Okay. Which we already saw by choosing rules appropriately for expanding these mists. This is going to be the same as just this negative white, black, negative black, white, negative black, black. And now, what we've been told is that if there's a spider behind the door that matches the color of the cube, then a knot is going to happen on the ball. Okay. So take for the moment that there's no spiders at all. Well, then nothing happens to here. Okay. Because remember, the rules are just like, you kind of just run through the configurations and apply the rules separately to every configuration. But if there's no spiders at all, nothing happens. Okay. So then I drop this mist through the spider testing computer, and nothing changes. So in fact, it's still the same as this. Okay. And then I have these two peak boxes at the bottom. And a peak box just undoes the thing that made this mist here. Okay, this is a calculation I've done in excruciating detail with students before this. So basically the peak box, when I drop this through these two peak boxes, this was the mist that you got by taking a black ball into the peak box, and this was the white ball. So it's kind of like the spider box did nothing, and I've just dropped a black ball through two peak boxes and a black cube through two peak boxes. So what I get out is just a black ball and a black cube. Okay. And I'm going to claim that this tells me that there are no spiders, that it's safe to press the open button and open the doors. So what we want to be sure of is the fact that if there are spiders behind either one of these doors, then we will not see both the ball and the cube black. That one or the other of them is going to look white. So how does that work? Well, if we look at what the mist is, the sort of quantum state or misty state, and we say, take for example the case that there are spiders behind the black door. Okay, then spiders behind the black door. Well, this is the point in the mist where the door is black. Okay. And so now I'm going to have a not operation applied to the ball at these points in the mist, because there's spiders behind the black door. And so now my mist evolves to something like this. So I've applied a knot here and here. And now if you say, what happens when I put this thing through two peak boxes? Okay. Well, I'm running slightly short of time, but it's basically, this mist here is the equivalent of, and this is a bit like factorizing numbers when you do arithmetic. It's basically the equivalent of this. You can check by expanding. And when I put this through a peak box, I get out a white cube. Okay. This I get out a black ball. So I've discovered that there are spiders in the system, because if there were no spiders, I would have seen two black objects come out. But you can go through and check for the other case that if there's spiders behind the white door, again, you will see a white cube. And that is actually the very most basic, in fact, the first quantum algorithm that David Deutsch came up with, just done as a single qubit algorithm, or two qubit algorithm. And it can be extended, as I say in the book, to really make clear that there's that you can get an exponential gap for this kind of problem between what you would be able to do with the classical computer and what you will be able to do with the quantum computer. And here we see that the only difference between the classical and the quantum computer is just the addition of these peak boxes. Okay, so now I just want to talk for a little bit about that. Because that's, I think, okay, so let me just say a few other things. There's many misconceptions about quantum computing out there, and I think with this simple example you can actually remove almost all of those misconceptions. So one example of a misconception with quantum computing is that it's about smaller and faster gates. Okay. But here we see that the separation has nothing to do with the speed of how the computation happened. It's really to do with the number of steps in the computation. That's the difference between quantum and classical computing, that you can come to a situation where it doesn't matter if the quantum gates operate much slower than the classical gates. There are going to be problems that just use so many fewer steps in the quantum case that you will rather go with a slower gate speed than a faster gate speed. Okay. That's a common misconception. Another common misconception is that quantum computers compute uncomputable things. And it's easy to remove that misconception because here, I just did it on a piece of paper. I did the computation. So it means that there is a computable function which will do the computation that any quantum computer will do. It's just that it's inefficient, as you saw me drawing out all of that stuff. It's the difference is a difference of efficiency. It's not a difference of whether something is computable or not. And then you can sort of, there's many other misconceptions. Oh, well, the computation's happening on, many alternatives all at once. Really, what someone will see when they go through this is what the key is this interference, is this negative sign that lets things cancel out. And that's basically, the whole story for what's the difference in power between quantum and classical computers. Okay. So as I finish, I just want to, I've talked about essentially a formalism, and I'll show you the book, and you can sort of learn more of the formalism. But what I didn't do very well in this talk, and I think, I tried to do it in the book, every time I teach, I still feel kind of, I've really got to emphasize it. The problem when you're writing a book is the book is full of figures. In fact, let me stop showing you this. If you go to the web page for Q is for Quantum, you can download the book, right? The book's full of figures, very similar stuff to the kind of stuff I've shown you already. And lots of calculations of these lists and so on. But what's difficult to separate is what is the mathematics and what is the physics of the descriptions that you're giving. If I had, more time and money and could publish a book in color or something, I would draw the physical setups like 3D and colored or something. And then the mathematics would be stuff like this. Because there's big problems when we teach physics in general, but quantum mechanics in particular, when we confuse the mathematics for something that's in the real world. And this is true in undergrad quantum mechanics teaching, never mind, trying to teach high school students. So I really want to be able to keep a separation between, what is the mathematics that you are writing down in order to compute what it is that you think will happen in this experiment. What is your prediction for what's going to happen in this experiment? And the problem with figures like the one, with the sort of thing that I've just shown you is, or things like this, is that there's sort of a confusion of like the peat box that I draw on a piece of paper and the peat box that I build in the real world. Okay, and when you're in a book and drawing diagrams and sort of restricted in your color schemes and certainly restricted by your artistic ability, then making sure that students appreciate that distinction is difficult. It's a little bit easier when you're giving talks because you can just sort of keep hammering it home with them. But another thing I tried to do in the book is not bias people with interpretations. And I think as soon as you start reifying different pieces of the mathematics of quantum theory, you start biasing students already with different interpretational frameworks. So, if any of you decide to pick up on any of this stuff and run with it, I would just implore you, do not sully the minds of young people with some sort of scrambled omelet of bits of mathematics and bits of physics and waves, are these waves in real space, are these waves not in real space, and so on. Like, just try and keep those things separate. Last thing to say, there's a website for the book, and I'm sorry I've sort of run us out of time. I have a few more minutes to answer questions. The FAQs on the website will answer, I think, a bunch of questions you might have about, like, is the system really universal? I didn't have complex numbers. How the heck can I be doing stuff with complex numbers? What about degrees of freedom that aren't binary? What about time? All sorts of other things. So, and I'm also very happy to answer emails and to, just try and help people use this formalism, which I think is actually a very powerful way of teaching quantum theory. So I'll leave it at that. Thank you.
Thank you. This is very interesting. One thing that we want to be sure that we follow on is you mentioned at the beginning when we started discussing whether you could give this talk or not, that there are a number of high school teachers that have used this already. Is there any way to follow and find out how it worked for them?
I mean, I sort of have contact details for some people. Most of the people have done it as, you know, sort of 4 to 6 hour like summer camp type, or, you know, extension courses for some of their brightest students, and normally small classes, 5 or 6 people. I'm very happy to give talks, and I do to such classes. There's a high school teacher who I've just been talking with in Germany, who's got the same last name as me, although we're not related. And he just translated into German a kind of mini course that Sophia Economy and Ed Barnes put together, which teaches some of the stuff. And you know, I'm working with Sophia and Ed to try and you know, some of their group to try and make, just, you know, we need more material. Like, if we really want to teach the stuff, you need proper teaching materials. You need exercises and solutions and things like that. And, you know, the way I present things in the book, look, I was locked in a dormitory in Rwanda for a couple of weeks, and it was, you know, it's not maybe to everyone's style, the way the sort of narrative that I came up with, but I think the techniques themselves are powerful, because it's a universal set of rules for quantum computing that really matches only the rules of basic arithmetic. But yeah, I guess the only other thing I would implore people to do is never start teaching quantum mechanics or even this kind of version of quantum mechanics by just listing all the rules. And that was how my quantum mechanics was taught to me in my 3rd year, and we spent 10 lectures first learning all the rules of the mathematics of Hilbert space. I think it's always better to just try and go through what is operationally observed, and then how do we explain it? What's another thing we observe operationally, how do we explain it? So that people can see that the rules are not just sort of, that's how we discovered them. And, you know, they're not just sort of, you know, sucked out of thin air.
Okay, I think we should take some questions. I think Celia needs to go, but the question is, if she leaves, then the host disappears and the talk collapses.
Well, I think I can leave without ending the meeting. I certainly won't leave if that's not the
You
case.
can leave me as host, Celia. if you
Okay, and it may stop the recording, but at least we got
That'll
the
be
bulk
okay.
of that. And maybe Mary can start the recording again, so.
All right, thank you so
Very
much.
much, Terry. Yeah, I know there's questions, and I hope you can stay a little bit longer. Maybe we can have you back at another meeting. We really appreciate this perspective. And you know, this group is really trying to think about quantum education quite broadly and to scale things. And we have a lot of participants from across, you know, the whole quantum ecosystem. So if there's anything that you would advise to us, we'd love to hear that as well. So I really appreciate your time today. And good luck with the quarantine. I know I've watched others go through it. There is a light at the end of the tunnel. So
Thanks.
So I have a question. Okay, Terry. So so how do you teach? I mean, in simple way. I mean, for example, using this language. I mean, I can imagine I can translate, but I would like